Welcome our next speaker to the stage, which is Martin Leib. Martin Leib studied theoretical physics at the University of Constance. He holds a PhD in this same subject from the Technical University Munich, and he had postdoc positions in Tokyo, Scotland, and Innsbruck. He's currently employed at the Volkswagen Data Lab, and he's working there as a senior quantum algorithm scientist. Welcome, Martin. And your presentation today is titled "Beating Classical Heuristics for the Binary Paint Shop Problem with the QAOA." So for those in the audience who are already a bit wondering, QAOA is the abbreviation for the Quantum Approximate Optimization Algorithm, but I guess you're gonna tell this yourself to us in a moment. Welcome to our stage, Martin, and I hand over directly to you.
Yeah, thank you for the nice introduction, and thank you for inviting me. I hope you can all hear and see me. Yeah, okay,
yes, we
perfect. So as already introduced, I'm going to talk a little bit about a quantum application that we identified and also investigated a little bit. And but first and foremost, I want to tell you a little bit about the thought process that led us to this specific application. So I need to okay. So now typically when you read a popular science article about quantum computing, you hear, okay, quantum computing can do everything. It can cure cancer, it can speed up the nitrogen fixation process, and of course that is not true, even though the quantum computer might play a role in all of these things. And it really needs a lot of expertise to identify an application that is really amenable to a quantum speedup, because that in the end is what we are really aiming for, to solve a problem faster than we can with classical algorithms. And within this smaller group of problems that are really amenable to a speedup, there is another subdivision between an exponential and a polynomial speedup. And the paradigmatic example for an exponential speedup that everyone knows is Shor's algorithm and the factoring, the integer factoring problem. But if you aren't a Bond villain, that is not really a quantum application for you. And so if you are a serious businessman, you might be interested in a subroutine of the factoring algorithm, which is the quantum phase estimation. And you can use quantum phase estimation, for example, for quantum simulation. And that could help you to simulate a small molecule that is part of a medicine, or simulate a catalyst that is necessary for nitrogen fixation. Or you can, in some circumstances, even speed up linear algebra. And that opens a whole range of applications. So starting from machine learning to solving partial differential equations. And apart from that, you also have this polynomial speedup. And the paradigmatic example here is searching for a marked element in an unordered database. And typically when I tell people that, so they ask me, so why would I want to search through an unordered database? I'm building up this database in an ordered fashion to not search through an unordered database. And typically the application thought of here is in the following way. So think of a combinatorial optimization problem, for example, the Turing-Salesman problem, and you will build up this database of all possible routes this Turing-Salesman can actually take. And you're interested in finding the shortest one. That would be something you can directly map to a Grover search algorithm. And the problem, however, again, is that you only have this polynomial speedup. And this polynomial speedup actually applies only to the Grover search algorithm is kind of a meta algorithm. So it assumes that you can access an unordered database efficiently. And in this step, how to really access the database, there can be a polynomial overhead hidden, which is eating away your actually polynomial speedup. So what you really need to aim for in this NISQ era, and also in this era where we have fully error-corrected quantum computing, but very small quantum computers, is you would be heading for an exponential speedup. So what if as VW, you are interested anyway in combinatorial optimization problems. And the thing where we hope to find super polynomial or even exponential speedup is if you're actually not interested in the optimal solution, as in the Grover search case, but in a good approximation. So, and that is more of like an industrial use case. So you would, you already have some good solution that you get from a classical fast heuristic, and you want to improve on that. So you want to see if you can find a faster solution, a cheaper solution, or a solution that just gives you happier customers. And then you look, okay, how much is the difference, and does this difference justify paying the premium on really running a quantum algorithm instead of a classic algorithm? And that is basically what we are interested in. Really looking at approximating combinatorial optimization problems. So far for the quantum application. So now, if you have found an application, you need to identify an algorithm. And the guiding principle for us is really the capabilities of current state-of-the-art hardware. And we are, as you heard, in this noisy intermediate scale era where we have quantum computers that have qubits that are error prone. So they have some characteristic time T1 where they completely lose their information, and they have another time scale which is T2 where they somehow lose their quantumness. And whichever time is smaller, within this time window, we really need to execute the entire program. So what we are searching for is a constant time algorithm, because these are the ones we can really run on state-of-the-art hardware. And by constant time, I have to be a little bit more specific. So typically we think, or normal problems, we assume that if I increase the size of the problem, also your runtime will be longer. Yeah, but we cannot use algorithms on a state-of-the-art quantum computer to solve this kind of problems. We really have to execute a program that is constant time and does not depend on the system size. And so these types of algorithms, so typically one uses hybrid quantum classic heuristics for that. And these are algorithms that are a little bit set up like a neural network. So you have a couple of parameterized gates, and you execute these gates and you get some result. And you have some function that somehow finds out the quality of these results, and you adjust the parameters such that the quality of the results improves. And because of this heuristic classical quantum scheme, you typically don't have any performance guarantees, and that is a problem. So as I'm going to show you later on, if you really execute something on a QPU today, you will get results that are in some way underwhelming. And you need to have some assurance that what you're doing currently will lead you to a result that is better than classical for future generations. And for that, we actually need something like a speed up proof. And I'm going to show you to what extent we were actually able to find that with the binary paint job problem. So what is this binary paint job problem? So first of all, think of a paint shop in a factory, and the task is to paint cars that are given in a sequence that is, for all intents and purposes, random, and you cannot change this sequence. But you know that within this sequence, there are pairs of cars, always pairs of cars. So in this sequence, for example, we have 2 Porsches, 2 Golfs, 2 Bullies, and 2 Beetles, even though we don't produce them anymore. And if you stopped really, if you paint all these cars, in the end, you need to have, for every pair, one of these cars needs needs to be red and the other one needs to be blue. And the thing you can actually decide is when the first car of a pair enters the paint shop, you can decide what color to use to paint this car. If the second car arrives, you have to paint the other color. And now what you need to optimize is the number of color changes while painting this exact sequence of cars in the given form. And so why do you need to optimize the color changes? So typically we have one set of painting robots in these factories, and a color change would mean you have to flush out the old color, you have to clean the nozzles, you have to flush a new color, and well, this wastes paint, this pollutes water and takes time. So in the end, that all costs money, and we want to optimize the number of colors. And okay. This is just one paint sequence that is possible, and you can already see this is the optimal one because it only has one color change. Now, by now, I hopefully have convinced you that VW should be interested in that problem because it's really central to our operation, and in almost exactly this version appears in our factories in our day-to-day business. And so why are we as quantum algorithm designers interested in that? So the interesting thing about that problem is actually NP-hard. So it belongs to this class of problems where also the traveling salesman is, and job shop scheduling and bin packing. And now that basically means you cannot solve it to exhaustion with a classic algorithm. But as I told you before, that is also very unlikely to happen with a quantum algorithm because you only have this polynomial speedup. But if you're interested in approximation to the problem, you might be more successful. And from that perspective, this problem is also interesting because it's APX-hard. That means it's difficult to even approximate, to come up with a good approximation for that problem. Now, for this problem, there exists a couple of heuristics. So algorithms that are simple and are specifically constructed for this problem. And the first and most simple algorithm for that would be the red first. So you just start painting these cars, and every time you encounter a car that is the first of its pair, you just paint it red. And when the second car comes, you paint it blue. And you can, because this algorithm is very simple, you can prove an average performance for that, and that would be 2 color changes every third car. You can get a little bit more sophisticated than that, and that would be the greedy algorithm, and then you just start with 1 color and you change when necessary. That means you change when there is a second car of a pair, and you change only if you haven't changed already. And you can, again, prove that with that technique, you get 1 color change every second car. And you can think of a more complicated version. I'm not going into detail how this works. And this would be the greedy recursive. And with this, you can actually show that you have 2 color changes every 5th car. And now with QAOA, the quantum approximate optimization algorithm, we can show that we can provide, on average, better performance in constant time. And that is remarkable because all these algorithms that I showed you before have a runtime that is growing with the system size. And you can beat all of them with a constant time quantum algorithm that has not been specifically developed for this problem. And okay, so how do we do it? I will spare you the technical details, but if you are interested, please contact me after this talk. So the steps that you have to go through is, first you have to map this problem to a spin glass problem, and then you can solve this spin glass problem with a quantum approximate optimization algorithm. And the quantum approximate optimization algorithm is basically a spectroscopic version of quantum annealing. And spectroscopic would mean you divide the time it takes for quantum annealing into steps. And there are different versions of QAOA. depending on the number of steps. So there's basically a p equals 1, that means a one-step QAOA algorithm, a p equals 2, a two-step QAOA algorithm. And the more steps you have, the better your result should be. This is one of these algorithms, as I mentioned earlier, of this hybrid quantum classical flavor. So you have these parameters, which are basically the length of these time steps, and you adjust the time steps such that the results are better. And in our case, that would be the measure for the quality of the results would be the average number of color changes that you get. And you optimize for that. And actually in prior work, and also I'm going to spare to you the details here, please contact me afterwards, we showed that you can reformulate that problem specifically for the binary paint job such that you get rid of this outer optimization loop, so this classical part. And that is also very important to know because that speeds up this algorithm considerably. And now here we see the results of that. So we, what we do here is we generate random instances of these binary paint job problems. That means we generate random sequences of cars, and we develop this QAOA circuit for that. We simulate, or we actually calculate the average performance of QAOA in that case and plot it here as a function of the number of cars. And you can see the average number of color changes grows linearly with the number of cars. And the slope of this linear graph actually depends on the number of time steps we take for the QAOA. And it gets better and better the more steps we take. And if you look at this inset, you can see that we can actually beat, for example, the greedy algorithm with a QAOA algorithm that has 4 of these time steps. And we can actually extend this calculation to an infinite size problem. So we can actually extract analytically the performance in the infinite size limit for QAOA. And with that, we can show that p equals 1, so the one-step QAOA algorithm can beat random guessing, which is the minimum thing it should do. And with p equals 2, you can beat the red first, as I introduced before. With the p equals 4, you can beat the greedy algorithm. In p equals 7, you can even beat this recursive greedy algorithm. And that, again, to emphasize, that means you can beat classic algorithms with polynomial time with a constant time quantum algorithm. And these constant time quantum algorithms should be really executable on day-to-day on this current state QPUs. And we did actually another thing. So we did some experiments on an IonQ quantum computer. And so again, we build random instances, we execute them on a QPU, and we compare actually the performance of this QPU to a noiseless QPU that we can simulate because the systems are small enough. And with here, you can, in this plot, you can actually see that starting from 2 to 8 cars, you get some results from the QPU, but from 9 to 11, you basically get results that are not discernible from random guessing. And that is the basic message that I said. So current state hardware gives you not underwhelming results, and you really need to be sure that the future generations will give you some speed up. So with that, I would like to conclude and await your questions.
Thank you so much, Martin. Very interesting, very application-oriented, very illustrative. I think everyone can understand here why this approach is useful. Also, I, as a physicist myself, always enjoy seeing origin plotted graphs in presentations. I think we don't have much time for questions. There's one question I can see from the audience, so let me just read this out to you. Not knowing much about QAOA, my question is, can you give some intuitive insight into why the length of the quantum algorithm does not change when the problem size increases? Is the number of used qubits also constant?
Okay, so the number of used qubits is not constant. The number of used qubits actually grows with the system size. So every car you have, every pair of car actually you have in the sequence corresponds to 1 qubit. So the size of the QPU has to grow, but not this coherence time and not also not the decay time. That is kind of the central message here. To give some intuition why this works, that is very difficult. So we just so the number of steps is just fixed, and we can calculate the performance for that, and we found out it does that. Some intuition? No, I don't have any intuition why this should work.
That's fine. Thank you very much anyway for the answer. If you have more questions, I mean, you as the audience here, feel free to join Martin for the next 15 minutes in the Speaker's Corner. Once again, thank you very much. And we had